Far beyond the orbit of Earth, past the asteroid belt and the giant storms of Jupiter, Saturn carries with it a moon hidden beneath a permanent orange haze. For centuries, nobody knew what existed underneath that atmosphere. Telescopes showed only a blurred amber sphere suspended in the cold darkness beyond the inner solar system. No visible surface, no oceans, no weather systems, just haze. What was eventually found underneath that haze is one of the most disorienting places in the solar system. Titan has rivers, lakes, coastlines, and rain. It has weather systems and seasons. It has a thicker atmosphere than Earth's, but the rivers run with liquid methane. The lakes are filled with natural gas, and the rain falls through air, cold enough to kill a human being in seconds. Every feature that makes Titan feel familiar is built from something that should make it feel deeply alien, and that was before the James Webb Space Telescope looked at it. What Webb detected in Titan's atmosphere has not been fully explained. The signal was confirmed. It was not an error, and it has left researchers sitting with questions about this moon that the current models of how Titan works simply cannot answer. Titan was already one of the most scientifically interesting objects in the solar system before this finding. The finding made it something else entirely. Tonight, we go into what Webb found, what it means, why it matters, and why this particular moon has started to feel like a question science is not yet equipped to answer. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. Let's start with the moon hidden beneath Saturn's haze, and the mission that first revealed what was waiting underneath. A faint orange point moved beside Saturn. That was all anyone could see for centuries. Through the telescopes of 17th century Europe, Titan revealed no surface, no storms, no detail at all. Just color, just distance. In 1655, Dutch astronomer Christian Huygens noticed that point of light shifting beside Saturn night after night. He called it Luna Saturni, Saturn's moon, because no other moon around the planet had yet been identified. One moon was enough to change astronomy forever. Titan is immense, larger than Mercury by diameter, though much lighter in mass. Its width reaches roughly 5,149 kilometers across, while Mercury spans about 4,879. But Mercury is dense with metal. Titan is built from rock and frozen water ice, layered together beneath an atmosphere thicker than Earth's. And that atmosphere changes everything. At the surface, the pressure reaches nearly 1.5 times what you are breathing right now. You could stand there without a pressure suit. The air itself would not crush you, but the temperature would. Titan rests near negative 179 degrees Celsius, cold enough that water becomes as hard as stone and ordinary chemical reactions slow almost to silence. The moon circles Saturn every 15.9 Earth days, staying roughly 1.2 million kilometers from the planet. From Earth, the distance is staggering. At closest approach, Titan still remains around 1,200,000,000 kilometers away. A radio signal traveling at light speed takes nearly 68 minutes to arrive there. Every command humanity sends enters a long silence before anything answers back. Gravity feels gentler there, strange and slow. Titan's surface pull is only about 1/7 of Earth's, meaning you would weigh roughly 14% of your normal weight while standing beneath the haze, and above you, the haze never truly clears. Titan's atmosphere is made mostly of nitrogen, around 95%, remarkably similar to Earth, but mixed into it are methane and larger organic compounds, carbon rich molecules drifting through the sky in layers of orange smog. Sunlight barely penetrates the upper atmosphere. Visible light scatters away before reaching the ground. For generations, that haze hid everything below it. Telescopes saw only a blurred amber sphere suspended beside the rings. Then, in 2004, the Cassini-Huygens spacecraft arrived and began using radar, radio waves capable of passing through the atmosphere, to map the surface underneath. Months later, the European-built Huygens probe detached from Cassini and descended slowly through Titan's atmosphere beneath a parachute. On January 14th, 2005, it reached the ground and transmitted for 72 minutes before falling silent. What came back did not look dead. It looked hauntingly familiar. The first radar images arrived as bands of light and shadow, quiet data at first glance, nothing dramatic. Scientists inside the mission team stared at monochrome strips crossing Titan's hidden surface, waiting for patterns to emerge from the haze that visible cameras could never penetrate. Then the shapes became recognizable, not alien, familiar. Thin channels branched across the terrain like river basins seen from orbit above Earth. Dark coastlines curved around enormous bodies of liquid. Flat plains stretched between elevated ridges. Near the equator, long parallel streaks appeared in the radar maps, eventually resolving into vast dune fields running across the surface for hundreds of kilometers. Everything looked geological. That was the unsettling part. The forms made immediate sense to the human eye because we already knew landscapes like these. Rivers branch in predictable ways. Shorelines curve according to gravity and erosion. Wind organizes dunes into repeating structures. Titan obeyed all those rules, but the materials were wrong. The rivers were carved by liquid methane, not water. The dunes were not grains of silica sand drifting through dry air. They were organic particles, carbon rich compounds slowly falling from the atmosphere before gathering into ridges under Titan's winds. Even the seas were unfamiliar beneath their recognizable coastlines, filled not with water but with liquid methane and ethane resting at temperatures near negative 179 degrees Celsius. Planetary scientist Jonathan Lunine later described the feeling as profound disorientation. You were looking at a world that behaved like Earth while being assembled from entirely different chemistry, and the scale was enormous. Krakenmare spread across roughly 400,000 square kilometers near Titan's North Pole, making it larger than the Caspian Sea on Earth. Nearby sat Ligeia Mare, covering around 126,000 square kilometers, along with Pungamar farther east. Hundreds of smaller lakes surrounded them, scattered across the polar terrain like dark mirrors beneath the haze. Far to the south, Ontario Lacus rested near Titan's southern pole, spanning roughly 15,000 square kilometers. But around its edges, radar detected stranger features still, faint outlines resembling empty lake beds, dry basins, places where liquid once existed and no longer remained. Titan was changing in real time. That realization settled slowly across the mission. These landscapes were not ancient fossils locked in ice forever unchanged. Liquids moved there, winds shaped terrain, shorelines shifted, material flowed across the surface through processes still active beneath the orange sky. Cassini had arrived expecting a distant moon frozen into stillness, but the radar revealed a living landscape, one continuously reshaped by weather, chemistry, and time, moving at unfamiliar speeds. Rain falls slowly on Titan, almost delicately. A methane droplet drifting through that dense atmosphere descends at roughly 1.6 meters per second, far gentler than rainfall on Earth. You could nearly watch individual drops floating downward through the orange air, but they are enormous. Some methane raindrops reach almost 9.5 millimeters wide before breaking apart, nearly twice the maximum size of ordinary water droplets on Earth. Titan's weak gravity allows surface tension, the force holding liquid together, to maintain larger drops without tearing them apart during descent. The strange part is how familiar the system becomes once the rain lands. Methane evaporates from the northern seas under faint sunlight, rises upward through Titan's atmosphere, cools at altitudes around 30 kilometers, and condenses into clouds before falling again across the surface. It is a weather cycle almost identical to Earth's water cycle in structure. Only the chemistry has changed. And chemistry changes everything. The rivers flowing across Titan are not streams of water cutting through rock. They are channels carved by liquid natural gas moving across frozen water ice, harder than granite at these temperatures. Cassini's radar traced branching river systems extending hundreds of kilometers toward the polar seas, forming drainage networks that matched terrestrial river basins with uncomfortable precision. During its descent, the Huygens probe photographed dark channels weaving through brighter terrain below. The patterns were unmistakable. Liquid had flowed there repeatedly over long spans of time, reshaping the landscape through erosion, just as rainfall reshapes valleys on Earth. But Titan's climate does not behave evenly. Near the poles, methane rain falls more steadily, feeding lakes and seas through slow seasonal cycles. Closer to the equator, rainfall becomes rare and violent. Some regions may remain dry for years before sudden methane storms release intense floods across the terrain, cutting deep channels through the surface before vanishing again into evaporation and darkness. In 2010, the Cassini-Huygens mission observed one of these storms directly in Titan's southern hemisphere. Radar images showed large areas darkening after rainfall, then slowly brightening again as methane evaporated back into the atmosphere. Weather was not merely possible there, it was active, ongoing, and slower than ours on Earth. A water molecule spends roughly 9 days in the atmosphere before returning to the surface as rain. On Titan, a methane molecule evaporating from Kraken Mare may remain suspended within the atmospheric cycle for years before falling again. That slowness stretches across everything on Titan. Clouds evolve gradually. Rivers reshape terrain over immense spans of time. Entire seasons last more than 7 Earth years. But hidden inside this calm cycle is a growing problem. Sunlight continuously breaks methane molecules apart high in Titan's atmosphere, destroying them permanently through ultraviolet radiation. The methane rains down, it evaporates, it circulates again, and yet it should already be gone. High above Titan's clouds, sunlight is quietly dismantling the atmosphere. The process begins in the upper layers, where ultraviolet radiation reaches the methane gas drifting through the sky. Even this far from the sun, where sunlight is nearly 100 times weaker than at Earth, enough energy still arrives to break methane molecules apart, atom by atom. Slowly, continuously, hydrogen escapes first. It is light enough to drift upward into space, lost permanently to the vacuum beyond Titan's gravity. The remaining carbon fragments collide with nitrogen in the atmosphere and begin forming larger organic compounds, complex carbon rich particles that descend gradually through the haze before settling across the surface. The chemistry only moves one way. Methane enters the cycle, organic material comes out. Nothing naturally rebuilds the methane once sunlight destroys it. Every year, Titan loses more of the gas sustaining its weather, clouds, and lakes, and the numbers become impossible very quickly. Current atmospheric models estimate Titan's methane supply should survive somewhere between 10 million and 100 million years before depletion. Even the most generous estimate reaches only a tiny fraction of Titan's actual age. The moon itself formed roughly 4.5 billion years ago, alongside the rest of the solar system. By every ordinary calculation, Titan should already be dry. But when we observe the atmosphere today, methane remains everywhere. Clouds still form, rain still falls. The northern seas still contain vast reservoirs of liquid hydrocarbons beneath the haze. We are seeing an active methane world that, according to the chemistry, should have lost this atmosphere billions of years ago. So something is replacing it. One possibility lies beneath the crust itself. Scientists call it cryovolcanism, meaning volcanic activity involving ice instead of molten rock. A cryovolcano could erupt mixtures of water, ammonia, and methane from Titan's interior, releasing fresh methane back into the atmosphere through fractures in the surface. The Cassini-Huygens mission spent years searching for direct evidence of these eruptions. Several structures appeared promising, especially Sotra Patera, a deep depression nearly 1,700 meters deep, surrounded by elevated terrain resembling volcanic features on Earth. But no active eruption was ever confirmed. Another possibility involves clathrates, frozen cage-like structures where methane molecules become trapped inside water ice lattices, repeating crystal frameworks that can store gas under pressure for immense spans of time. If Titan's crust warms or fractures, methane could slowly leak outward from these underground reservoirs. More recently, researchers proposed a deeper source still. Inside Titan's hidden subsurface ocean, water may react chemically with rock and carbon-bearing minerals, producing methane through processes similar to those occurring near hydrothermal systems on Earth's ocean floor. The chemistry works in theory, but direct evidence remains absent, and that absence matters. Titan's methane budget still refuses to balance. The atmosphere persists, the destruction continues, yet the replenishment mechanism remains invisible, hidden somewhere beneath layers of ice, chemistry, and time. Far below the dunes and methane rain, Titan carries another world entirely. You would never see it from the surface. The crust above is immense, a shell of frozen water estimated between 50 and 100 kilometers thick. At Titan's temperatures, that ice behaves less like brittle frost and more like solid rock, compressed under enormous pressure into layers harder than concrete. But beneath it, something moves. Not methane, not ethane, liquid water. Scientists believe Titan hides a global subsurface ocean buried under the frozen crust, mixed with ammonia and trapped in darkness for billions of years. Ammonia matters because it acts like antifreeze, lowering water's freezing point and allowing liquid to survive in temperatures that would otherwise lock the ocean solid. The evidence comes from gravity itself. As Titan orbits Saturn, the moon flexes slightly under the planet's tidal pull. Tidal flexing means the shape of Titan changes as gravity stretches it during close orbital positions and relaxes it again afterward. The effect is small, only subtle distortions, but the Cassini-Huygens spacecraft measured those distortions carefully across multiple flybys, and the numbers did not fit a solid world. Scientists quantify this flexibility using something called the love number, a measurement describing how strongly a planetary body deforms under gravity. Titan's measured value, known specifically as the H2 love number, turned out far too high for an entirely frozen interior. Something beneath the crust had to be moving independently from the shell above it. Liquid explained the motion best. Some models estimate this hidden ocean may extend between 200 and 500 kilometers deep. If those estimates are correct, Titan could contain more liquid water beneath its surface than all of Earth's oceans combined. And strangely, the temperatures are not impossible for chemistry. Researchers estimate parts of the ocean may remain between -10 and 0 degrees Celsius, maintained by heat slowly released from radioactive elements inside Titan's rocky core. Uranium, thorium, and potassium decay over immense spans of time, producing radiogenic heating, the gradual warming created by radioactive breakdown deep inside planetary interiors. But the ocean may also be sealed away almost completely. Unlike Europa, where scientists suspect material occasionally moves between ocean and surface through fractures, Titan's ice shell appears far thicker and more stable. The crust may isolate the ocean below from the atmosphere above, with almost no exchange between them. And that creates something extraordinary. Two entirely separate chemistry systems appear to exist on the same moon at the same time. Above the crust, sunlight drives atmospheric reactions that produce complex organic compounds drifting slowly onto the surface through the haze. Below the crust, liquid water sits under pressure beside rock and dissolved minerals in total darkness. The two environments may have remained separated for billions of years, and still, both continue operating quietly beneath Titan's orange sky, each following completely different chemical rules. From a distance, Titan does not look like a world with weather or surface at all. It appears as a single suspended glow, a muted orange sphere hanging in Saturn's orbit, as if the entire moon is wrapped in a permanent atmospheric veil. That color is not surface reflection. It is chemistry in motion. What we are seeing is tholin haze. Tholins are complex organic compounds, meaning carbon-based molecules formed through repeated chemical reactions rather than a single stable substance. They are not one material. They are an entire family of thousands of different structures created when ultraviolet light breaks apart methane and nitrogen in Titan's upper atmosphere. Fragments collide, recombine, grow larger, slowly, endlessly. The term was introduced by Carl Sagan in 1979. He chose a word meaning muddy because laboratory simulations of planetary atmospheres kept producing the same result, a thick, brownish residue that refused to fit any standard chemical category. It was not simple enough to name easily. It was too complex to classify cleanly. Above Titan, the process begins high in the sky. Formation starts above 200 kilometers altitude, where solar radiation and energetic particles from Saturn's environment continuously break molecular bonds. The fragments do not disappear. They rearrange into larger structures, building from simple gases into increasingly complex organic particles. These particles become aerosols, tiny solid grains suspended in gas. They begin a slow descent. The fall is not fast. It takes years to reach the surface. During that descent, each particle continues reacting with trace gases it encounters along the way, gradually changing composition as it moves through different atmospheric layers. Chemistry continues even while it falls. Eventually, the haze settles onto Titan's surface. Everything is coated. Ice bedrock, mountain slopes, lake shores, and dune fields all receive a continuous layer of organic sediment. Nothing is spared. Over geological time, this coating builds into thick accumulations of carbon-rich material spread across the entire moon. The equatorial dunes are especially striking. They are not made of sand in the terrestrial sense. They are made of compressed tholin grains shaped by wind into long, linear ridges, some stretching up to 100 kilometers in length and rising nearly 100 meters above the surrounding plains. Together, these dune systems cover roughly 17% of Titan's surface. And inside these particles, something important appears. Laboratory experiments recreating Titan's atmospheric chemistry consistently produce tholins that contain precursors to amino acids, meaning molecular structures that could, under different conditions, form the building blocks of life as we know it, not life itself, but the ingredients arranged in the right direction. This haze also hides everything beneath it. Visible light cannot pass through Titan's atmosphere. Most infrared wavelengths are scattered or absorbed long before reaching the ground. For centuries, the surface remained invisible. But not entirely. The instruments aboard the James Webb Space Telescope were designed to operate in narrow infrared windows where the haze becomes partially transparent. In those specific wavelengths, light can pass through gaps in the atmospheric absorption, revealing details hidden from earlier missions. It was through those windows, in 2022, that something unexpected appeared in Titan's atmosphere. Before we ever touched Titan's surface, the equator already looked structured. Not chaotic, not random, structured like something that had been organized by time itself, stretched across a planet we had never directly seen. When the radar maps from Cassini began to resolve the equatorial band, long parallel formations appeared, repeating across thousands of kilometers without breaking their rhythm. They were dunes, and they were enormous. The equatorial dune fields span an area roughly twice the size of the United States, forming continuous ridges that wrap around Titan's middle latitudes. Each ridge runs in long east to west alignments, creating a planetary pattern that feels almost deliberate when viewed from orbit. But nothing about them is deliberate. These structures are built from tholins, complex organic particles formed in the atmosphere and deposited slowly over time. A tholin is a carbon-rich grain produced when methane and nitrogen are broken apart by ultraviolet light, then recombined into heavier molecules that eventually fall to the surface as solid organic dust. Over billions of years, that dust becomes terrain. Individual dune ridges measure about 1 to 2 kilometers in width and rise roughly 100 meters above the surrounding plains. Spacing between them remains remarkably consistent, typically between 1 and 4 kilometers, suggesting long-term atmospheric winds have shaped them with steady persistence rather than short bursts of activity. Those winds are not random either. Titan's near-surface circulation is influenced by tidal interactions with Saturn, which subtly organizes atmospheric motion across the equator. The same gravitational relationship that drives methane weather also guides how organic grains are pushed across the surface, aligning the dunes into their global orientation. The scale of material involved is difficult to compress into Earth-based comparisons. The total carbon locked inside these dunes is estimated to exceed all known oil and coal reserves on Earth combined. Yet there is no combustion here, no oxidation, no fire. Titan's atmosphere lacks oxygen entirely, so this massive organic reservoir remains chemically stable, accumulating layer after layer without being consumed. Each grain is small, around 2 to 300 micrometers in diameter, similar to fine terrestrial sand. Cassini's infrared spectrometer confirmed that their composition matches laboratory-produced tholins almost exactly, linking the dunes directly to atmospheric chemistry rather than local geology. Between these organic seas of sand, gaps appear. Radar data shows bright patches where water ice bedrock breaks through the dark coating, revealing the underlying structure of Titan's crust. These exposures suggest the dunes are not a uniform blanket, but a shifting layer, moving across an older frozen world beneath. And then there is the surface itself. When the Huygens probe reached the ground, it found rounded ice cobbles resting in a field of dark sediment. stones shaped by ancient methane flows, now sitting motionless under billions of years of atmospheric deposition. Nothing about this landscape is static. Everything is built from motion that has already passed, frozen into place, while the atmosphere above continues to rewrite it grain by grain. Nothing on Titan begins complex. Everything starts with the simplest gases drifting through a cold, orange sky. Methane, a molecule made of one carbon atom and four hydrogen atoms, and nitrogen, two nitrogen atoms bound tightly together in a stable pair. These are ordinary ingredients scattered across the outer solar system. But on Titan, nothing stays ordinary for long. High above the surface, ultraviolet light from the sun and charged particles from Saturn's radiation belts begin breaking those molecules apart. This process is called photodissociation, meaning light-driven molecular splitting. Hydrogen atoms are stripped away first, leaving behind highly reactive fragments known as radicals. They do not remain separate. They collide immediately, driven by chemistry that never rests. Carbon bonds with carbon bonds with nitrogen. New structures begin forming in a constant microscopic exchange across the upper atmosphere. The first stable products are small molecules: acetylene, ethylene, ethane, hydrogen cyanide, simple compounds with only a few atoms each, yet already carrying the first steps of complexity. Cassini detected these molecules in abundance throughout Titan's atmosphere, and later measurements from the James Webb Space Telescope confirmed their persistent presence with greater clarity and resolution. From here, the ladder rises. Acetylene reacts with hydrogen cyanide to form cyanoacetylene. Ethane interacts with nitrogen radicals to form nitriles, a class of carbon-nitrogen compounds that behave as chemical bridges between simple gases and more complex organic structures. Each reaction builds slightly larger molecules, each step introducing new possibilities for further transformation. Slowly, accumulatively, nitriles hold particular scientific interest because on early Earth they are believed to have contributed to the formation of nucleobases, the molecular letters that form DNA and RNA. These are not biological structures themselves, but they represent chemical pathways that can lead toward biology under different conditions. Titan runs this chemistry continuously. Driven by solar energy and Saturn's particle environment, nitrile production operates across the entire atmosphere for billions of years. No interruption, no reset, just persistent layering of complexity in a cold, nitrogen-rich sky. But the ladder does not stop there. Further reactions produce polycyclic aromatic hydrocarbons, large ring-shaped molecules composed of fused carbon structures. These compounds gradually aggregate into aerosols, eventually forming the proto-tholin particles that create Titan's dense atmospheric haze. At the highest altitudes, Cassini's ion and neutral mass spectrometer recorded molecules exceeding 1,000 atomic mass units. These are extremely large organic structures, too complex for individual classification, representing a level of chemistry that approaches macromolecular behavior in the ionosphere above 400 kilometers. And somewhere within this layered system, something does not fit. Webb detected an anomalous signal in the middle atmospheric region, an altitude range where existing models predict smoother chemical transitions rather than unexplained concentration spikes. It does not match known pathways cleanly, which suggests a missing step in the ladder, a rung we have not yet seen. Light reached Titan carrying instructions encoded in wavelengths of infrared radiation. It had traveled for more than an hour through deep space, unchanged in form but stretched across distance. On November 4th, 2022, those photons entered the instruments of James Webb Space Telescope, beginning a new level of atmospheric reading for Saturn's largest moon. NIRCam, the near-infrared camera, recorded spatial structure by isolating specific infrared bands where Titan's haze becomes partially transparent. NIRSpec, the near-infrared spectrograph, separated incoming light into extremely fine wavelength components, a process known as spectroscopy, where individual molecules leave identifiable absorption patterns in light. Together, they did not just image Titan, they translated it. Every wavelength became a trace of altitude, composition, and motion within the atmosphere. Each reading corresponded to a different layer, allowing scientists to sample chemistry at multiple heights without touching the world itself. The data arrived as streams of numbers, but each stream represented a physical depth in Titan's sky. Within hours, those streams revealed something active. Two large cloud systems appeared over the northern hemisphere, bright and evolving. These were methane clouds, formed through convection, the upward movement of warmer gas that cools and condenses into droplets at higher altitude. They sat above regions influenced by seasonal heating near polar seas, marking a shift into northern summer conditions that had not been fully observed since earlier mission phases. Their brightness changed between frames, confirming movement rather than static reflection. The team immediately extended observation efforts. Ground-based telescopes were contacted for confirmation, including facilities capable of infrared tracking through Earth's atmosphere. Follow-up measurements confirmed that the clouds had shifted position within 48 hours. The atmosphere was not only active, it was changing on observable timescales across interplanetary distance. Then the spectral analysis deepened. NIRSpec data revealed the expected chemical landscape first. Methane absorption lines appeared exactly where long-term models predicted. Ethane signatures matched previous Cassini measurements. Acetylene features aligned with known atmospheric chemistry pathways driven by ultraviolet breakdown of methane in the upper layers. The system behaved as expected across most wavelengths, reinforcing confidence in decades of prior atmospheric modeling. But at specific altitudes, between roughly 50 and 200 kilometers above the surface, something diverged. A narrow absorption feature appeared in the lower stratosphere. An absorption feature is a dip in light intensity at a specific wavelength caused by a molecule absorbing that energy. This one did not correspond to any known compound in Titan's atmospheric database. It persisted across multiple observations, remained stable under recalibration, and did not match expected methane chemistry byproducts. The signal was real, and it resisted classification. Repeated checks eliminated instrument error. Cross-comparison with laboratory spectra found no direct match. Even known trace gases failed to reproduce the pattern at that altitude range. The atmosphere remained consistent everywhere else, but this single layer carried a signature that current models could not place. Something in Titan's middle atmosphere was absorbing light in a way no existing framework had predicted, sitting quietly between known chemistry layers, unresolved and persistent across time. The first explanation always feels simple until it is not. After weeks of spectral reduction and cross-comparison, the most consistent match for the strange absorption pattern was a molecule called propionitrile, also known as ethyl cyanide. Its chemical formula is C2H5CN, a chain of carbon, hydrogen, and nitrogen atoms forming one of the many nitrile compounds found in cold space chemistry. On paper, it should not be surprising. Propionitrile has been detected before in interstellar environments, including dense molecular clouds such as Sagittarius B2, where complex organic molecules accumulate under low-temperature radiation-driven chemistry. It belongs to a family of compounds that naturally arise wherever carbon rich gases are exposed to energy over long timescales. Titan's models even allow for it. In theory, propionitrile forms when ethyl radicals, highly reactive carbon fragments, combine with hydrogen cyanide in the upper atmosphere. From there, it should drift downward slowly, dispersing in extremely low concentrations as it mixes through atmospheric layers. That is the expected pathway. But Webb did not see expectation. It saw placement. The signal appears in Titan's lower stratosphere, a region between roughly 50 and 200 kilometers above the surface, where photochemical production is weaker and chemical reactions slow as sunlight fades through the haze. In this zone, models predict that propionitrile should thin out, not accumulate. Instead, the opposite appears. The concentration implied by the spectral strength is significantly higher than current atmospheric chemistry models allow, not slightly off, not within uncertainty bounds. Outside the expected range by a margin that cannot be resolved through calibration or noise correction alone. So the question shifts: where is it coming from? One possibility is that an unknown reaction pathway exists in the lower stratosphere, a chemical sequence not yet included in Titan's atmospheric models, producing propionitrile locally under conditions we have not replicated in laboratories. Another possibility is upward transport, a mechanism that lifts molecules from the surface or lower atmosphere back into higher layers against the expected gravitational and diffusion gradients. A third possibility sits deeper still. Surface or cloud level chemistry may be producing propionitrile directly, feeding it into the atmosphere in ways that bypass known formation routes entirely. Each option requires new physics or chemistry not currently confirmed. None of them are established. The research team treated the detection carefully. The identification was published as a candidate match, not a confirmed assignment, with explicit acknowledgement that the source mechanism remains unknown. But the signal itself held steady. A second feature appeared in the same dataset, a separate absorption line in a different wavelength range, not matching propionitrile or any other known Titan atmospheric compound. It remains unassigned in published literature, described only as an unresolved spectral feature requiring further laboratory comparison. Follow-up observations in 2023 confirmed both signals persisted. They were not transient, not noise, not a one-time event. They remained embedded in Titan's atmosphere, unchanged across time, waiting for an explanation that has not yet arrived. Some discoveries are not new because the universe changes. They are new because we finally look differently. When the Cassini-Huygens mission studied Titan, it was already pushing the limits of early 21st century instrumentation. Its infrared spectrometer, the Composite Infrared Spectrometer, known as CIRS, was designed to measure heat and broad atmospheric composition across Saturn's system. It could map gases. It could infer structure. But it was never built to resolve the finest chemical fingerprints hidden in faint spectral lines. Resolution mattered, not in a general sense, but in a physical one. Cassini's spectral resolution blended nearby absorption features together, turning multiple overlapping molecular signals into a single broadened curve. Many subtle compounds became indistinguishable from background haze. Then came the shift. The James Webb Space Telescope carries NIRSPEC, the near-infrared spectrograph, a system with spectral resolution roughly 10 to 100 times higher in key wavelength ranges. That increase does not simply sharpen data. It separates chemistry that previously looked identical into distinct molecular signatures. It is like hearing individual instruments inside a single blurred chord. Position also matters. Webb operates near the Sun Earth L2 point, a gravitationally stable region about 1.5 million kilometers from Earth. This location keeps the telescope thermally stable, shielded from Earth's infrared noise, and free from atmospheric distortion. Ground based telescopes must constantly correct for Earth's atmosphere. Webb does not. But Titan adds another layer of advantage. Its haze is not uniform. It contains specific infrared transparency windows, particularly around 2.0, 2.7, and 5.0 micrometers. In these ranges, light can pass through different atmospheric depths, allowing Webb to effectively sample Titan's atmosphere layer by layer. Each molecule responds differently to infrared light. Molecular bonds vibrate at specific energies, creating absorption features that act like fingerprints. These fingerprints do not change with location or altitude. A methane molecule on Titan absorbs light in the same pattern as one in a laboratory on Earth. That consistency allows precise identification when resolution is high enough to separate overlapping signals. And Webb's sensitivity reaches levels Cassini could not approach remotely. It can detect trace gases at parts per billion concentrations, capturing atmospheric chemistry at scales previously invisible. Cassini's instruments did detect complex molecules directly, but only during close flybys through the ionosphere above 880 kilometers, where the spacecraft physically passed through the gas itself. Webb does something different. It observes from 1.2 billion kilometers away and still resolves chemical structure in the stratosphere between 50 and 200 kilometers altitude, a region Cassini could sense but not fully dissect. That layer is now where the anomalies appear. This is not a correction of Cassini. It is a continuation of it. Each instrument opens a different depth of the same world. Cassini revealed structure. Webb reveals separation within that structure. And for the first time, Titan's atmosphere is no longer a single blurred envelope, but a layered chemical system where unexpected signals can finally be isolated from the noise around them. Above Titan's haze, the sky changes character entirely. At roughly 400 kilometers altitude, the atmosphere stops behaving like a simple gas and begins behaving like an electrical environment. This region, called the ionosphere, is a layer where solar ultraviolet radiation and charged particles from Saturn's magnetosphere strip electrons from molecules, creating ions, meaning electrically charged atoms and fragments, alongside highly reactive radicals. Nothing here stays stable for long. The ionosphere stretches upward beyond 1,500 kilometers, forming a vast zone of continuous chemical disruption. It is not calm chemistry. It is collision-driven transformation, where every interaction produces new reactive pathways faster than equilibrium can form. During its close passes, the Cassini-Huygens spacecraft briefly entered this region using its ion and neutral mass spectrometer. What it recorded changed the upper boundary of Titan's chemical understanding. Organic molecules appeared at unexpected scales. Some exceeded 100 atomic mass units, already far beyond simple atmospheric fragments. But in several measurements, signals rose above 1,000 atomic mass units, placing them in the range of small polymers, meaning chain-like structures composed of repeating molecular units. At that scale, molecules begin to resemble the precursors of complex prebiotic chemistry rather than simple atmospheric byproducts. But the mechanism driving this growth is what matters most. Ion-neutral chemistry. The interaction between charged ions and neutral molecules dominates this region. Unlike slower neutral reactions driven only by ultraviolet light, ion driven reactions proceed rapidly and without strict selectivity. This allows complex structures to assemble quickly under energetic conditions that would normally prevent stability. And Titan's position inside Saturn's system makes this even more dynamic. When Titan moves through Saturn's magnetosphere, streams of energetic electrons accelerate ion production, intensifying chemical reactions in the ionosphere. When it briefly exits that environment, the dominant influence shifts toward the solar wind, altering reaction pathways and producing measurable changes in molecular composition. Cassini observed these variations directly. Different ionospheric compositions appeared depending on Titan's orbital position, showing that space weather is actively shaping atmospheric chemistry in real time. The ionosphere is not a static layer. It is a constantly rewritten chemical interface between planetary atmosphere and cosmic environment. From this region, molecules begin their descent. They drift downward through hundreds of kilometers of atmosphere, passing through temperature gradients and density changes that gradually slow their motion. As they fall, they continue reacting, growing larger and more complex as they encounter new gases and particles. By the time they reach lower altitudes, many have already transformed into the building blocks of Titan's haze. These particles eventually settle as tholins, the organic material coating the surface. And somewhere along that descent lies the altitude where Webb's anomaly appears, a middle layer between creation above and accumulation below, a region shaped by both ionospheric energy and atmospheric chemistry, yet not fully explained by either. The ionosphere forms the top of Titan's chemical ladder. Webb is reading the middle, and beneath everything, the surface waits, with its own chemistry still untouched by what begins far above. Season on Titan does not feel like change. It feels like slow atmospheric drift across decades. The cause is simple in geometry. Titan follows the same axial tilt system as its parent planet Saturn, whose axis leans about 26.7 degrees relative to its orbital plane. That tilt drives seasonal cycles in sunlight distribution, just as it does on Earth. But the time scale is completely different. Titan's orbital period around Saturn is roughly 29.5 Earth years. One full Titan year lasts nearly 3 decades. Each season stretches across about 7.4 Earth years, unfolding slowly enough that entire mission lifetimes can sit inside a single climatic phase. When the Cassini-Huygens arrived in 2004, Titan was deep in southern summer. The southern hemisphere dominated atmospheric activity. Storm systems clustered near the South Pole, feeding a large and persistent polar vortex. Meanwhile, the northern hemisphere remained relatively quiet, its weather systems muted and sparse. Everything was asymmetrical. But that asymmetry was temporary. By 2017, when Cassini ended its mission, Titan was shifting towards seasonal balance. Northern regions began to warm in sunlight exposure, cloud formation increased, and the southern polar vortex weakened, slowly collapsing as energy input changed across hemispheres. Then came a gap. Years passed without close atmospheric spectroscopy at comparable resolution. Titan continued its slow seasonal transition without detailed chemical monitoring from orbit, until late 2022, when the James Webb Space Telescope began observing Titan. The moon was entering northern summer. This is a phase where sunlight reaches higher northern latitudes more directly, driving increased atmospheric circulation, enhanced methane evaporation, and stronger cloud formation above polar seas. It is also a phase no previous high-resolution spectroscopic mission has fully captured. This matters because seasonal chemistry is not uniform chemistry. During Cassini's southern summer, an unexpected atmospheric event occurred. A cloud composed of dicyanoacetylene ice formed at roughly 300 kilometers altitude above the South Pole. Dicyanoacetylene is a carbon-nitrogen compound predicted to exist in gas form, but never expected to condense into solid particles under those atmospheric conditions. The temperatures at that altitude were considered too warm for such a phase transition. Yet it happened. A mismatch between prediction and observation, and it remains one of the earliest hints that Titan's stratospheric chemistry does not always follow equilibrium expectations. Now Webb is observing the opposite hemisphere under opposite seasonal conditions. Northern summer brings increased solar exposure and dynamic polar activity, which may amplify chemical pathways that remain weak or absent during other seasons. The anomalous signals detected in the stratosphere could be partly seasonal in origin, strengthened by atmospheric circulation patterns unique to this phase of Titan's long year. Even after 13 years of Cassini data, the seasonal chemistry is still not fully understood. The spacecraft never witnessed a complete Titan year from start to finish, and its instruments lacked the spectral resolution needed to isolate subtle stratospheric features at the level Webb now achieves. So Webb is not just observing Titan with better tools. It is observing a different moment in Titan's long climate cycle. And in that timing, the atmosphere may be revealing processes that were always present but never before seen under these specific conditions of light, temperature, and motion. Somewhere between land and liquid, Titan stops behaving like a single system. The shoreline is not a boundary here. It is a meeting point where chemistry layers overlap and begin to interfere with one another. At the edges of Ligaea Mare and Kraken Mare, liquid methane moves across frozen terrain coated in tholin deposits, the organic residue that has been falling through Titan's atmosphere for billions of years. Nothing stays separate for long. Methane acts as a solvent, a liquid capable of dissolving certain non-polar organic compounds. It is not as versatile as water, but it still carries chemical potential. At the shoreline, it seeps into the upper layers of tholin-rich sediment, partially dissolving complex organics and transporting them into the liquid environment where new reactions become possible. The interface becomes active. Dissolved tholins interact with methane-ethane mixtures inside the lakes, forming intermediate compounds that would not exist in either the dry atmosphere or the isolated liquid alone. These reactions are slow, extended across time scales far longer than terrestrial chemistry, but they are continuous under Titan's stable conditions. Cassini observations suggested something even stranger. At the surface of some lakes, faint radar signatures hinted at a thin layer of material, possibly an organic film. A surface scum is a very thin accumulation of substances that float at the boundary between liquid and air. On Titan, such a layer may consist of heavy organic molecules, too dense to dissolve fully, yet too light to sink. But beneath that surface, the lakes remain largely hidden. Cassini-Huygens radar measured depths in Ligaea Mare reaching around 170 meters at sampled points, but could not resolve the composition of deeper layers or the structure of the lake floor. What lies at the bottom remains unobserved directly. Models suggest a stratified system. Ethane, produced continuously by atmospheric chemistry, is denser than methane and tends to sink. Over time, it may accumulate in deeper layers, creating a compositional gradient where methane dominates the upper liquid while ethane and dissolved organics concentrate below. This layering would slowly reshape the internal chemistry of Titan's largest seas, and the shore does not remain fixed. During northern summer, increased solar energy drives stronger evaporation cycles. Methane levels fluctuate, and shorelines shift outward or inward depending on seasonal balance. As liquid retreats, previously submerged sediment becomes exposed, suddenly interacting with ultraviolet light for the first time in long periods, allowing new surface reactions to begin before being covered again. Cassini recorded similar behavior at Ontario Lacus in the southern hemisphere, where the lake visibly shrank between 2005 and 2010 as seasonal conditions changed. The movement was slow but measurable, a reminder that Titan's liquids are not static bodies but dynamic systems responding to orbital time. At the shoreline, three worlds overlap at once. Atmosphere, liquid, and solid surface converge into a single narrow zone where chemistry is constantly rewritten. On no other known world do all three environments interact so quietly, for so long, without interruption. A scar on Titan does not last long. Across the mapped surface of Cassini-Huygens data, fewer than 100 confirmed impact craters appear, an unexpectedly small number for a moon that has existed for 4.5 billion years. Early solar system history should have left a heavily pockmarked surface. Instead, Titan looks partially erased. The reason is steady resurfacing. Methane rain reshapes terrain over long cycles. Organic particles fall continuously from the atmosphere. Occasional cryovolcanic activity may resurface regions with fresh ice. Together, these processes slowly bury or soften impact scars before they can remain clearly defined. The surface behaves less like a record and more like a living system of slow replacement. Even the largest confirmed structure, Menrava, spanning roughly 440 kilometers, appears degraded. Its rim is no longer sharp, its basin softened by time and sediment. What remains is a memory of impact rather than a preserved crater shape. But the moment of impact itself is where something unexpected begins. When a large asteroid strikes Titan's icy crust, the energy release is extreme. In an instant, ice behaves like rock under pressure, then fractures and melts under heat. This creates a transient pool of liquid water at the impact site, a rare state on a moon where surface water cannot persist under normal conditions. The duration is brief. Liquid water at Titan's surface temperature remains stable only for hundreds to thousands of years before refreezing. In planetary terms, this is a fleeting interval, barely a blink against geological time. Yet within that window, chemistry becomes radically different. The melt pool interacts directly with surrounding organic material. Tholins, the complex organic compounds coating Titan's surface, dissolve partially into the water. Dissolution is the process where solid molecules separate and disperse into a liquid medium, allowing chemical reactions that would otherwise remain impossible in frozen conditions. Under these conditions, hydrolysis occurs. Hydrolysis is a reaction where water breaks chemical bonds, transforming complex organic material into simpler, biologically relevant molecules. Laboratory experiments replicating this environment consistently produce amino acids such as glycine, alanine, and aspartic acid. These are not precursors. They are complete amino acids, the same molecular building blocks found in proteins on Earth. As the impact pool cools, the newly formed molecules become trapped within refreezing ice. Each layer preserves a chemical snapshot of that short-lived environment, locking the products into place as additional organic sediment slowly accumulates above them over time. Titan has experienced thousands of such impacts across its history. Each one may have briefly recreated conditions favorable for complex chemistry. Each one may have produced amino acids under natural, repeated circumstances. And those chemical records remain buried, distributed across a surface that is constantly being rewritten. Somewhere among them, one of the youngest craters holds the next opportunity for direct measurement. Some places on Titan feel like they are waiting to be read. Among them is Selk, a crater about 90 kilometers wide, sitting near 7 degrees north latitude close to the equatorial region. It is not ancient enough to be erased, and not young enough to still look fresh. Instead, it sits in a narrow window where chemistry may still be legible beneath the slow accumulation of organic fallout. The surface around it tells a quiet story of preservation. Data from Cassini-Huygens revealed exposed water ice within Selk's structure, an unusual signature on a world where most ice is buried under thick layers of tholin deposits. Water ice exposure suggests that the impact excavated deeper material and that resurfacing processes have not fully concealed it yet. But Selk is not just a scar. The impact that formed it released enough energy to melt water ice instantly, producing a transient liquid water environment inside the crater. A hydrothermal event is a short-lived period of heat-driven water chemistry created immediately after an impact, when subsurface ice briefly becomes liquid before refreezing. During that interval, the surrounding organic material would have interacted directly with liquid water. Laboratory simulations of this exact sequence consistently produce amino acids. As the crater cooled, that liquid environment would have frozen again, trapping newly formed molecules inside ice layers that preserve chemical history with remarkable stability over geological time. Each stage becomes a locked record of a brief but intense chemical experiment. This is where Dragonfly enters the story. The spacecraft carries DRAMS, the Dragonfly Mass Spectrometer, a device that analyzes molecules by breaking them into charged fragments and measuring their mass. It is capable of identifying amino acids, nucleobases, and other complex organics with precision high enough to distinguish biologically relevant chemistry from background material. Its journey is not direct. Dragonfly will first land in the Shangri-La dune fields, where it will sample untouched organic sediment formed purely by atmospheric deposition. From there, it will begin a series of controlled flights across Titan's surface, gradually moving towards Selk over a mission timeline of about 2.7 years. Each landing site serves a different chemical layer. Dunes represent atmospheric output. Plains show redistributed material. Ejecta zones reveal excavated subsurface ice. The crater interior represents the final stage, where impact-driven chemistry may have once occurred under liquid water conditions. Powering this journey is a radioisotope system that converts heat from decaying plutonium into electricity, allowing continuous operation through Titan's long nights and low sunlight conditions. The atmosphere itself assists flight, dense enough to generate lift efficiently in a way impossible on most worlds. By the time Dragonfly reaches Selk, it will have built a continuous chemical map of Titan's surface history. Arrival is expected in 2034. By then, the questions raised from distant orbital spectroscopy will have traveled all the way down to the ground. And for the first time, those questions will be answered where the chemistry actually happened. Somewhere in Titan's long chemical history, something stopped matching the numbers. Methane in the atmosphere is constantly broken apart by ultraviolet light, a process called photochemistry, meaning light-driven molecular breakdown. In this reaction chain, methane splits into smaller fragments and recombines into heavier hydrocarbons, including ethane, a stable two-carbon molecule that does not easily break apart again under Titan's cold conditions. Over billions of years, this should have built up. Models suggest that at Titan's production rate, enough ethane would exist to form a global layer hundreds of meters deep, spread evenly across the surface. A planet-wide reservoir, slowly accumulating like a chemical memory written in liquid form, but the surface does not show it. Data from Cassini-Huygens revealed lakes and seas instead of a global ocean. Liquid bodies exist, but their total volume is far too small to account for the predicted ethane production over 4.5 billion years. The difference is not subtle, it is vast. This mismatch is known as the ethane deficit. It is a simple idea with uncomfortable implications. Ethane is detected, but only in limited amounts. It appears in lakes such as Ontario Lacus and within Ligeia Mare, confirming that it is part of Titan's active surface chemistry. Yet, the measured concentrations are consistently lower than models predict, especially in methane-dominated systems where ethane should gradually dominate over time. The expectation and the reality diverge sharply. In Ligeia Mare, methane remains surprisingly abundant compared to ethane, creating a liquid composition that appears younger than its calculated age. This imbalance suggests either hidden reservoirs or missing processes that remove ethane from the observable system. Several explanations exist, none confirmed. Ethane may be seeping into the ice crust, forming clathrates, which are cage-like structures where gas molecules become trapped inside water ice. It may be sinking into deeper subsurface reservoirs that radar cannot penetrate. It may be accumulating unevenly in polar basin floors, never fully sampled. Or the atmospheric models themselves may be overestimating production rates across geological time. Each option changes the interpretation of Titan's surface. The ethane deficit is not isolated. It links directly to the methane cycle, which also lacks a confirmed replenishment source. If methane is continuously supplied from below while ethane disappears into hidden reservoirs, the surface chemistry becomes part of a larger, incomplete cycle we cannot yet close. Nothing balances cleanly. This is not a small error in measurement. It represents billions of years of missing material, unaccounted for in a system that should be chemically consistent over time. Somewhere on Titan, the missing ethane must exist, either locked beneath the crust or redistributed in ways current instruments cannot resolve. And while orbital instruments cannot reach it, a surface mission like Dragonfly may eventually sample regions where that hidden material interacts with the surface, offering the first chance to close a chemical equation that has remained open since Cassini's first measurements. Nothing on Titan begins in isolation. Every ridge, every lake, every chemical cycle is shaped by an invisible hand. That hand belongs to Saturn, whose gravity does more than hold Titan in orbit. It continuously reshapes how the moon behaves, from deep interior structure to surface weather patterns. The connection is mechanical and constant. Tidal forces are differences in gravitational pull across a body. On Titan, these forces stretch and compress the moon slightly as it orbits Saturn, creating internal friction. That friction becomes heat. Not dramatic, not explosive, but steady and persistent over billions of years. This slow heating helps maintain a subsurface ocean in liquid form, working alongside radiogenic heat from radioactive decay inside the rocky core. Without both sources, Titan's internal water layer would likely freeze completely. But the influence does not stop underground. The atmosphere itself responds. Near surface winds show patterns influenced by Saturn's gravitational pull, creating subtle tidal circulations that guide long term wind direction. Over geological time, these persistent flows shape the orientation of dune fields, leaving behind directional records written in organic sediment. Even rainfall carries this imprint. Titan's methane cycle, which governs cloud formation and precipitation, is influenced by atmospheric tides. These are slow periodic bulges in atmospheric density caused by Saturn's gravity, which alter where clouds form and how storms develop across hemispheres. The result is not random weather, it is structured variability. Above it all, Saturn's magnetosphere extends outward, a vast magnetic field filled with charged particles. As Titan passes through this environment, energetic particles collide with its upper atmosphere, driving ionosphere chemistry. Ion formation is the process where atoms lose or gain electrons, becoming highly reactive and capable of building complex organic molecules. Without this external energy input, Titan's atmospheric chemistry would be far less active. Measurements from Cassini-Huygens revealed something even more subtle. Titan is slowly drifting away from Saturn at roughly 11 centimeters per year. That outward migration suggests that tidal interactions are still actively transferring energy between the two bodies, gradually reshaping their orbital relationship. Over billions of years, that distance matters. In the distant past, Titan would have orbited closer to Saturn. The tidal forces would have been stronger, the interior warmer, and cryovolcanic activity potentially more frequent. Methane cycling may have been more vigorous, driven by enhanced internal energy and faster atmospheric turnover. Today's Titan may therefore be a quieter version of its own history, a reduced state of a more active world. What we observe now is not a snapshot of stability, but a stage in a long gravitational exchange that has never fully stopped. Even the chemical complexity present in its atmosphere may be the product of that earlier, more energetic era, preserved and slowly evolving under reduced forcing. Seen this way, Titan is not simply a moon orbiting a planet. It is a system still being written by that planet. And understanding Saturn becomes another way of reading Titan itself, layer by layer, across time that stretches far beyond human observation. Time can make two planets look unrelated, even when their chemistry speaks the same language. To understand Titan, we step backward in time, not outward in space. We return to early Earth, between 2.5 and 4 billion years ago, when the planet had not yet been transformed by oxygen or life. That ancient Earth is the closest analog we have to what Titan is doing today. The atmosphere then was simple but active. Nitrogen dominated the air, with methane present in meaningful amounts. There was no free oxygen. Ultraviolet light reached the surface directly, and electrical storms were common. These conditions created continuous chemical reactions driven by energy inputs that required no biology at all. Titan shares parts of this structure, but not the temperature. On early Earth, liquid water existed across the surface, acting as a universal solvent. A solvent is a medium that allows molecules to dissolve and interact freely. In that warm ocean environment, organic compounds could combine, separate, and recombine at high speed, creating increasingly complex molecular systems over time. On Titan, the same starting materials exist. Methane, nitrogen, and energy from ultraviolet radiation and Saturn's magnetosphere produce similar organic molecules in the upper atmosphere. These molecules fall through the sky as tholin particles, gradually coating the surface in chemically rich material. But their behavior changes upon arrival. Instead of dissolving into liquid water, most compounds on Titan settle into liquid methane or accumulate as frozen solids. Liquid methane is a non-polar solvent, meaning it does not interact easily with many complex organic structures. As a result, chemical reactions proceed far more slowly than they would on early Earth. Temperature controls everything. A general rule in chemistry suggests that reaction rates decrease significantly with falling temperature. On Titan, surface conditions are roughly 300 degrees colder than early Earth. That difference does not reduce chemistry to zero, but it stretches it across vastly longer timescales. Reactions that would take years on early Earth may take millions or even billions of years on Titan. Yet time is abundant there. Over 4.5 billion years, even extremely slow processes accumulate meaningful outcomes, and occasionally, impact events temporarily recreate early Earth-like conditions. When liquid water forms in impact craters, chemistry briefly accelerates to rates closer to those ancient terrestrial environments. Experiments conducted by Carl Sagan in the 1970s showed that when nitrogen methane mixtures are exposed to energy sources such as ultraviolet light or electrical discharge, complex organic molecules form spontaneously. These laboratory results demonstrated that prebiotic chemistry is not unique to Earth, but a natural outcome of certain atmospheric conditions. The implication is not that Titan resembles Earth exactly. It is that both worlds follow overlapping chemical rules under different constraints. One is fast and warm, the other slow and cold. And yet both are capable of producing complexity from the same simple ingredients given enough time and energy. Before life becomes anything recognizable, it passes through chemistry that looks almost ordinary. Prebiotic chemistry is the study of those early steps where simple molecules begin forming increasingly complex structures without any biological guidance. It is not life itself. It is the slow construction of possibility. On early Earth, the key ingredients included hydrogen cyanide, formaldehyde, acetylene, and a wide range of nitriles, which are carbon-nitrogen compounds that form stable chemical backbones. Many of these same molecules are present today in Titan, preserved in its atmosphere and surface chemistry. Some are especially important. Hydrogen cyanide is a highly reactive compound that acts as a starting point for multiple prebiotic pathways. In the Strecker synthesis, it contributes to amino acid formation, while in the Oro reaction, it helps produce adenine, one of the fundamental components of DNA. These reactions are not hypothetical. They are experimentally demonstrated chemical routes under plausible planetary conditions. Titan produces hydrogen cyanide in significant quantities. Data from Cassini-Huygens confirmed it as one of the most abundant trace gases in the stratosphere, continuously replenished through photochemical reactions, driven by ultraviolet light and charged particles from Saturn's environment. But hydrogen cyanide is only the beginning. Propionitrile, a more complex nitrile compound, sits higher in the chemical sequence. It forms when smaller reactive fragments combine and stabilize under specific atmospheric conditions. Laboratory simulations of Titan-like atmospheres have shown that compounds like propionitrile can form alongside molecular precursors to amino acids, especially when energy input and particle density reach certain thresholds. This is where the interpretation becomes careful. The presence of these molecules does not indicate biology. It indicates active prebiotic chemistry, meaning chemistry capable of producing increasingly complex organic structures without requiring life as a driver. The key implication of the James Webb Space Telescope detection is not confirmation of a specific molecule, but a shift in where and how that chemistry appears to operate. If propionitrile or related compounds exist in unexpected concentrations or altitudes, it suggests that Titan's chemical pathways are more dynamic than current models predict. More dynamic chemistry means more building blocks. Each additional precursor increases the probability of downstream reactions that could, under the right conditions, progress toward self organizing chemical systems. That phrase carries caution because conditions matter more than ingredients. On Titan's surface today, the environment is not favorable for Earth, like biological development, but conditions are not uniform across time. Inside impact generated melt pools. Transient liquid water creates short lived environments where hydrogen cyanide, dissolved organics, and hydrolyzed tholins can interact in ways closer to early Earth chemistry. These windows are brief, but chemically significant. Titan is not replicating Earth's path. Instead, it is exploring fragments of it repeatedly across vast spans of time. Each fragment may represent a partial step along a pathway that on Earth eventually led somewhere far more complex. Not every discovery announces itself clearly. After the attention drawn to propionitrile, another feature remained quietly embedded in the same dataset from the James Webb Space Telescope observations of 2022. It was a spectral absorption feature, a specific dip in infrared light caused when a molecule absorbs energy at a precise wavelength. This one did not match any known reference in Titan's chemical catalog. It was not expected. The signal appeared in the lower stratosphere, the atmospheric layer between roughly 50 and 200 kilometers above the surface. It was not aligned with propionitrile, nor with any of its chemical relatives. Instead, it sat isolated, unassigned, and unresolved. Follow-up observations in 2023 confirmed it. The feature remained stable, repeating under similar observational conditions, which ruled out simple instrumental error or transient atmospheric noise. That persistence made it harder to dismiss, but also harder to explain. In planetary science, unidentified spectral features are not rare. A spectral feature is the specific pattern of light absorbed by a molecule, acting like a chemical fingerprint. When no known molecule matches that pattern, it usually means either the molecule has never been measured under relevant conditions, or it has never been considered likely in that environment. Both possibilities carry implications. To identify the source, laboratory spectroscopists must recreate candidate molecules under Titan, like temperatures and pressures, then compare their absorption patterns against the observational data. It is a slow process, requiring controlled conditions, precise measurements, and iterative testing across many potential compounds. There is no shortcut. The importance of this particular signal lies in its location. The lower stratosphere of Titan was previously considered chemically stable compared to the highly reactive upper atmosphere. Most models predicted only gradual transport of simple molecules through this region, not active production or accumulation of complex species. But this feature suggests otherwise. If the signal originates from a molecule forming or persisting at these altitudes, it implies a chemical pathway that is not fully represented in current models. That pathway could involve cloud surface reactions, aerosol particle chemistry, or vertical recycling processes where surface-derived organics are lofted upward and reprocessed in the atmosphere. Each of these possibilities changes the structure of Titan's chemical system. The second signal is, in some ways, more intriguing than the first. Propiona trial fits within known chemistry, even if its distribution is unexpected. This feature does not. It remains without a confirmed identity, which places it in a different category of scientific uncertainty. Not absence of knowledge, but active incompleteness. As additional data from the Cassini-Huygens archive and ongoing Webb observations are integrated, the parameter space narrows. Each new spectrum either strengthens the persistence of the feature or reduces the list of possible molecular candidates. For now, it remains unresolved. A single line in the spectrum of a distant atmosphere, holding steady across years of observation, waiting for a match that has not yet been found. The end of a mission is never just a moment. It is a carefully shaped decision carried out across years of planning. On September 15th, 2017, the Cassini-Huygens began its final descent into Saturn's atmosphere. The spacecraft did not fail or drift into loss of control. It was deliberately guided into destruction to prevent any future accidental impact on Titan or Enceladus, where Earth microbes could have compromised planetary protection standards. The ending was as precise as the science that preceded it. In its final phase, Cassini completed 22 close orbits through the narrow gap between Saturn and its inner rings. No spacecraft had ever flown through that region before. It measured ring particle composition at close range, mapped magnetic field structures, and sampled atmospheric boundaries where Saturn's upper atmosphere begins to interact with space. Each pass reduced distance and increased risk. On its last Titan encounter, Cassini used the Moon's gravity to adjust its trajectory. That interaction redirected the spacecraft toward Saturn itself. Titan did not just appear in the mission's story. It helped determine its ending. The final transmission from Cassini reached Earth 83 minutes after the spacecraft had already been destroyed by atmospheric entry. For that short interval, the signal continued traveling through space, even though the instrument that produced it no longer existed. What Cassini left behind was not closure, but an expanded list of unknowns. The source of methane remained unresolved. The ethane deficit remained unexplained. Large ionospheric molecules detected in flybys were still unidentified. The subsurface ocean had never been directly sampled. Cryovolcanic activity remained unconfirmed. Even the dunes, while mapped, lacked full compositional resolution. Titan was more defined after Cassini, but also more uncertain. After the mission ended, a gap began. For 5 years, no spacecraft observed Titan with comparable sensitivity or resolution. The Moon continued its seasonal cycles, atmospheric chemistry, and surface processes without close inspection at that level of detail. Then the observation baseline changed again. In late 2022, the James Webb Space Telescope resumed detailed atmospheric study of Titan using high-resolution infrared spectroscopy. Unlike Cassini, which sampled directly or from orbiting passes, Webb reconstructed atmospheric chemistry remotely, layer by layer, from deep space. Its early results confirmed expected molecules, but also revealed spectral features that did not match existing models of Titan's atmospheric chemistry. Some could be partially explained, others remained unresolved. The shift was not in direction, but in resolution. Cassini had revealed structure. Webb revealed finer chemical detail within that structure. Together, they did not resolve Titan. They exposed how much of its system still operates beyond full explanation. The gap between missions was not empty. It was a period where Titan continued evolving without close measurement, its chemistry progressing while scientific understanding waited for new instruments. What followed was not a conclusion. It was the continuation of a system that was never fully mapped, only progressively revealed. The question begins not with certainty, but with constraint. On Titan, every possibility is narrowed by physics that moves slowly, coldly, and with extreme limits on chemical energy. The environment does not encourage complexity, it suppresses it. Any idea of life here must first survive those boundaries before it can even be considered plausible. In 2010, researchers Chris McKay and Heather Smith explored a strict theoretical model for methane based biology. Their work did not argue for life. It asked what life would be forced to become under Titan conditions if it existed at all. The proposal was specific. In liquid methane, organisms would likely use hydrogen as an energy source and acetylene as a reactive compound to metabolize. The byproduct of such reactions would be methane itself, released back into the atmosphere in a closed chemical loop. That idea immediately encountered a problem of scale. Data from the Cassini Huygens showed slight irregularities near Titan's surface chemistry. Hydrogen levels appeared lower than expected in some regions, and acetylene concentrations did not always match atmospheric production models. Both findings, however, have strong non-biological explanations tied to surface reactions and atmospheric transport. No observation required life. Every known pathway fits conventional chemistry, and yet the exercise remains important because it defines what would be required for biology to function, not what is likely, but what is barely possible. At minus 179 degrees Celsius, liquid methane behaves in ways fundamentally different from water. It does not support polar structures like phospholipid membranes easily. It slows molecular motion to near geological timescales. Chemical reactions that take seconds on Earth may take years or longer. A hypothetical organism in this environment would not resemble familiar biology. It would likely be microscopic, metabolically minimal, slow beyond intuitive comprehension, energy constrained to the point where growth, if it occurred at all, might be measured in decades rather than hours or days. Complexity would be a burden, not an advantage. But even this scenario carries a broader implication. If even one independent origin of life occurred within the same solar system, it would reshape assumptions about how common biology is across the universe. It would suggest that life is not a rare exception, but a recurring outcome wherever chemistry and time intersect under the right conditions. Most researchers remain cautious. The consensus expectation is that Titan's lakes are sterile. The energy budget is too low, the reaction rates too slow, the molecular pathways too restricted. Still, that conclusion is not absolute. It reflects probability, not impossibility. And Titan has repeatedly shown that its system does not always follow expected outcomes. Future exploration will test these limits directly. The Dragonfly carries the DRAMS, a system designed to analyze surface chemistry at fine resolution. It is not built to search for life specifically, but it can detect molecular signatures that would be difficult to explain without biological influence. On Titan, even the absence of expectation becomes a kind of data, and that is where the question remains suspended, unresolved, and scientifically open. In the cold distance of space, chemistry does not wait for planets. It begins earlier, quieter, and on scales far larger than any single world. Across interstellar clouds, carbon, nitrogen, and hydrogen interact under radiation fields that never stop. These are not stable environments. They are active chemical reactors spanning light years where molecules are built, destroyed, and rebuilt in endless cycles driven by ultraviolet light and cosmic rays. In the molecular cloud Sagittarius B2, astronomers have identified an unexpected richness of organic chemistry. Compounds such as hydrogen cyanide, cyanoacetylene, ethanol, glycoaldehyde, and even urea exist in measurable quantities. Some of these molecules are chemically simple. Others approach the complexity of early biochemical precursors. This is not a local phenomenon. It is a recurring pattern. When fragments of the early solar system were analyzed in the Murchison meteorite, scientists found more than 70 amino acids embedded in its structure. These molecules formed before Earth had stabilized, preserved in rock that predates biology entirely. The implication is direct but unsettling in its simplicity. Organic chemistry does not require life, it precedes it. Laboratory simulations reinforce this pattern. When mixtures of nitrogen, methane, and hydrogen are exposed to ultraviolet light, they produce complex organic residues known as tholins. These same reactions occur in conditions designed to mimic interstellar clouds and in simulations of Titan's upper atmosphere. The output is chemically similar, even when the environments are vastly different in scale and temperature. More recently, observations from the James Webb Space Telescope have extended this pattern further outward. Organic molecules have now been detected in protoplanetary disks, the rotating clouds of gas and dust where new planetary systems are forming. These are not mature environments, they are construction zones, still assembling the conditions for future worlds. The chemistry is already there. Before the planets arrive, what emerges from this accumulation of evidence is a structural conclusion rather than a localized discovery. Organic chemistry appears to be the default outcome whenever carbon, nitrogen, hydrogen, and energy interact over sufficient time. It is not confined to Earth, nor dependent on biology. It is a universal tendency expressed wherever the physical conditions allow it. In that context, Titan becomes more than a moon. It becomes a nearby example of a much larger process unfolding across the galaxy. Its atmosphere, surface, and lakes represent a continuous experiment in carbon-based chemistry operating at planetary scale, shaped by the same physical laws that govern molecular clouds tens of thousands of light years away. But what Titan adds is proximity. It is close enough to observe in detail, close enough to sample, close enough to test directly against theory. What happens there can be measured rather than inferred. And that changes the role of the question. It is no longer only about whether Titan is unusual. It becomes about how consistent chemistry is across environments that appear unrelated in scale, temperature, and structure. Titan does not stand apart from cosmic chemistry. It reflects it, and in doing so, it offers a rare opportunity to see the universe not as a collection of isolated worlds, but as a continuous chemical system still in motion, still building complexity wherever conditions allow. Arrival on Titan is not an arrival at certainty. It is a return to questions measured in chemical detail. When Dragonfly reaches Titan in 2034, nearly 3 decades will have passed since humanity briefly touched its surface through the descent of Huygens. In that time, no instrument has directly sampled Titan's organic world at ground level. Everything since has been inference, reconstruction, and spectral interpretation from orbit. Dragonfly will change the scale of that knowledge. Its mission begins in the Shangri-La Dune Fields, a vast equatorial region shaped by winds and coated in dark organic grains. These dunes represent the least altered material on Titan's surface, sediments that have fallen from the atmosphere and accumulated over millions of years without significant chemical reset by liquid water. This is the baseline. From there, Dragonfly will move in stages across a 175-kilometer path towards Selk Crater, each landing chosen to represent a different chemical history. Plains reshaped by methane rainfall, ejecta fields disturbed by ancient impacts, and finally, the crater interior, where transient liquid water once existed. At each site, the DRAMS will perform direct molecular analysis. It will vaporize surface material and separate it into components based on mass and structure, producing a detailed chemical fingerprint of each environment. This allows comparison against known signatures of amino acids, nucleobases, and other biologically relevant molecules. The expectation is not uniform across the surface. In impact regions like Selk, laboratory simulations suggest that hydrolysis of tholins in transient water should produce amino acids. If Dragonfly detects higher concentrations of these compounds in crater material than in the surrounding dunes, it would confirm that impact-driven chemistry repeatedly generates complex organics on Titan. But if those signals are weaker than predicted or absent entirely, that result would be equally important. It would imply either that the laboratory models overestimate chemical efficiency under Titan conditions, or that the products degrade or transform over geological time in ways not yet understood. Dragonfly will not only analyze chemistry, it will observe environment directly. Cameras will map surface geology at close range. Meteorological sensors will track atmospheric changes at ground level. A gamma-ray spectrometer will measure elemental composition without physical contact. And a seismometer will listen for internal activity, detecting possible ice shell movement or subsurface shifts that could hint at tidal or cryovolcanic processes. Each dataset will add a missing layer to what orbiters like the Cassini-Huygens and telescopes such as the James Webb Space Telescope have already suggested from distance. But this time, the data will not be interpreted through gaps. It will be measured at the source. And that distinction changes everything, because every model built from orbit eventually meets the same test on the surface. Whether Titan's chemistry aligns with prediction or diverges from it, Dragonfly will convert speculation into direct evidence. The results will begin arriving in 2034, slowly at first, then continuously, and once they do, the abstract chemistry of Titan will no longer remain remote or theoretical. It will become observed reality, written in molecules collected from the ground beneath its orange sky. Time moves differently when nothing interrupts it. On Titan, processes continue without pause, without observation, and without urgency. Liquid methane cycles through evaporation and rainfall across the northern seas, especially in regions like Krakenmeer, where vast hydrocarbon bodies quietly exchange material with the atmosphere above. Nothing about this system requires attention to continue operating. Above it all, organic haze persists. Particles known as tholins, defined as complex organic residues formed by ultraviolet processing of methane and nitrogen, drift downward from altitudes near 200 kilometers. They accumulate slowly across dunes, plains, and lake shores, building layers that change only over geological spans. Below the surface, an ocean of liquid water and ammonia remains hidden under ice, hundreds of kilometers thick. It flexes under Saturn's tidal pull, a process called tidal deformation, where gravitational forces cause periodic stretching and relaxation of a planetary body. That motion keeps the ocean from freezing completely, even in extreme cold. None of this stops. It simply continues. Meanwhile, the James Webb Space Telescope continues its distant observations. Each new dataset refines atmospheric models, constrains molecular candidates, and tracks seasonal change as Titan transitions through northern summer. The two anomalous spectral signals identified in earlier observations remain under study, either moving toward identification through laboratory spectroscopy or growing more complex as new data is added. Both outcomes carry weight. One resolves uncertainty, the other expands it. But resolution on Titan does not arrive quickly. The Dragonfly is already in preparation, scheduled for launch in 2028. Its journey to Saturn's moon will take roughly 6 years, crossing nearly 1.5 billion kilometers of space. During that time, Titan will continue its seasonal progression, moving from northern summer into autumn, altering atmospheric circulation and surface chemistry in ways that will not be directly observed in real time. By the time Dragonfly arrives in 2034, the Webb observations that defined its scientific context will already be more than a decade old. In that period, models will have been refined, debated, corrected, and expanded. Yet the original anomalies will remain part of the foundation that guided mission design. This is not unusual in planetary science. The timeline is consistent across generations of exploration. The questions raised by Voyager 1 during its Titan flyby in 1980 took decades to interpret fully. The findings from the Cassini-Huygens continue to generate analysis long after its mission ended in 2017. Titan resists immediacy. It accumulates time instead of surrendering it. Every process on its surface and beneath it unfolds at a pace that makes human observation feel compressed by comparison. Chemistry evolves slowly. Atmospheres shift gradually. Oceans remain hidden across entire mission lifetimes. 8 years until Dragonfly arrives is brief in that context. But for those waiting, it is a measurable span of uncertainty. And in that silence, between observation and arrival, Titan continues doing exactly what it has always done, running its chemistry, without interruption, without explanation, and without waiting for us to understand it. Sometimes the most important discoveries are not objects, they are inconsistencies. In the case of Titan, the anomaly revealed by the James Webb Space Telescope is not defined by a single molecule or a single confirmed reaction. It is defined by a mismatch between expectation and measurement, between chemical models built over decades and spectral signals that refuse to align with them. A compound appears at an altitude where it should not be efficient to form. Its concentration does not match predicted production rates. Its persistence suggests a process that is either incomplete in current models or entirely absent from them. That kind of result is not rare in science, but its location makes it meaningful. It occurs in the atmosphere of Titan, a world already known to host one of the most complex organic environments in the solar system outside Earth. A place where methane cycles through weather systems, where nitrogen-driven photochemistry produces vast arrays of organic molecules, and where surface deposits accumulate over billions of years without interruption. In such a system, a small mismatch becomes something larger, not evidence of life, not even evidence of direction, just evidence of more happening than expected. The ingredients involved are not unusual. Carbon, nitrogen, hydrogen, and energy are among the most abundant building blocks in the universe. What matters is not their presence, but what they produce when given time. Titan demonstrates that even without biology, these elements generate structured, layered, and persistent complexity. The implication is subtle but broad. If models underestimate chemical production in a system as well observed as Titan, then those same models may underestimate chemical productivity elsewhere across icy moons orbiting gas giants in other systems, across interstellar clouds where radiation drives molecular assembly, across environments that have never been directly sampled. This is where the anomaly becomes interpretive rather than local. It becomes part of a longer pattern, from the detection of organic compounds in meteorites studied in the 1960s to the identification of complex molecules in interstellar clouds in later decades, to unexpected chemistry revealed by Cassini Huygens at Titan's surface, and now to stratospheric signals recorded in 2022. Each step has expanded the apparent range of what natural chemistry can produce. None of these discoveries required biology, but all of them increased the perceived richness of non-biological chemistry. That distinction matters because it means complexity itself is not rare. It is emergent. It arises whenever conditions allow energy to flow through simple elements over long periods of time. The form it takes may vary, but the tendency remains consistent. Titan sits at the center of this realization. It is not an exception to chemistry. It is an example of chemistry operating at scale, under conditions that slow it down but do not stop it. And when we observe a gap between prediction and measurement there, it does not point directly to life, or design, or anomaly in isolation. It points to something more fundamental, that the universe may be more chemically productive than our current models allow. And Titan, with all its unanswered signals and slow unfolding reactions, is simply where that realization becomes visible enough to notice. Long after human instruments fall silent, Titan will still be there. The sun, in its distant future, will leave its stable state. In roughly 5 billion years, it will exhaust its hydrogen fuel and begin expanding into a red giant. Its outer layers will swell outward, pushing deep into the inner solar system, engulfing Mercury and Venus, and possibly reaching Earth before shedding its atmosphere into space. But Titan lies far beyond that immediate destruction zone. It will remain. As the sun expands, its luminosity increases, and the outer solar system begins to warm. This is not a sudden change, but a slow transformation driven by increasing solar output and shifting gravitational balance. Titan's surface, currently stabilized at minus 179 degrees Celsius, will begin to respond. At first, the change will be subtle. Then it will accelerate. Ice that has remained rigid for billions of years will soften. Methane cycles will collapse and reform under entirely new conditions. The balance of Titan's atmosphere will shift as thermal energy begins to dominate processes that were once driven only by weak sunlight and Saturn's distant influence. At a critical point in this evolution, surface temperatures may cross the threshold where water ice becomes liquid water. This is not methane or ethane, but true H2O in a stable, flowing state on Titan's surface for the first time in its history. A brief oceanic phase will begin. It may last hundreds of millions of years, possibly approaching a billion, depending on the duration of the red giant stage and the stability of Titan's orbit as the sun loses mass. During that window, the entire chemical archive of Titan will be activated. Layers of tholins, defined as complex organic residues formed through long-term atmospheric photochemistry, will dissolve into newly formed liquid water. Amino acids preserved in ancient impact craters will be released into solution. Hydrogen cyanide, accumulated over billions of years in the atmosphere and surface deposits, will interact directly with warm water in reactive environments similar to those that existed on early Earth. Every major chemical pathway Titan has developed in isolation will suddenly gain access to a solvent capable of accelerating molecular interaction. And that changes everything. Because liquid water is not just another environment, it is a reaction medium that enables complexity to reorganize itself rapidly, allowing chemistry to move beyond accumulation into transformation. Whether this leads to biology or remains an extended period of complex but non living chemistry is something no current model can determine. The variables are too many, the timescales too vast, the initial conditions too uncertain. But what is clear is the structure of opportunity. Titan will not be chemically static during this phase. It will be active in a way it has never been before. A world built for 4.5 billion years under cold methane chemistry will suddenly operate under conditions that resemble, in broad thermodynamic terms, early Earth. And all of it will occur after the sun has already begun its final transformation. By the time this warm interval arrives, Earth itself will likely no longer exist in any recognizable form. It may have been consumed, stripped, or rendered uninhabitable long before Titan reaches its peak chemical accessibility. In that distant future, Titan may become the longest running chemical experiment in the solar system, finally reaching a stage where its full inventory of organic material is active at once. A world prepared for a question that arrives too late for anyone to ask. It always begins the same way, with data that refuses to settle, a spectral line that does not belong, a ratio that drifts outside prediction, a model that works everywhere except where nature actually tests it. On Titan, those small deviations have accumulated into something larger than error. They have become structure waiting to be understood. Underneath every measurement lies a single question, repeated across centuries of observation and across every instrument we have ever built. Are we alone? Not in the sense of distance or civilization, not in the sense of contact or communication, but in the deeper sense that defines all of planetary science at its core. Is the chemistry that led to us rare? Or is it inevitable? Titan sits at the center of that uncertainty. At roughly 1.2 billion kilometers from Earth, it continues its cycles without interruption. Methane evaporates, condenses, and falls as rain across vast dunes of organic sediment. Tholins, defined as complex carbon-based molecules formed through atmospheric radiation chemistry, accumulate layer by layer across a surface that has never been biologically active, as far as we know. And beneath it all, an ocean of liquid water remains hidden under ice hundreds of kilometers thick, sealed from direct interaction with the surface but still dynamically shaped by Saturn's gravity. This is not a world waiting for discovery. It is a world already doing chemistry. The James Webb Space Telescope has added a critical piece to that picture, a spectral anomaly in Titan's atmosphere that does not align with existing chemical models. Not a contradiction strong enough to overturn theory, but a deviation persistent enough to demand explanation, something present that should not be there, or something missing that should be. Both possibilities lead to the same conclusion. Our understanding is incomplete, and incompleteness is not failure. It is the starting condition of exploration. The next step in that exploration is physical contact. The Dragonfly will arrive in 2034 and begin analyzing surface chemistry directly. It will collect organic material that has been accumulating since before complex life appeared on Earth. It will measure molecular masses, compare them to laboratory standards, and return results that will immediately reshape every model built from orbit. But no single result will be final. Each answer will expand the boundary of the next question. That is the pattern that has repeated from the earliest telescopic observations of Saturn through the flybys of Cassini-Huygens, and now into the era of deep infrared spectroscopy. Every improvement in resolution has revealed not closure, but additional layers of complexity. Titan preserves that pattern in extreme form. It does not resolve easily into simple explanations. It accumulates processes over billions of years and keeps them active in different layers, separated by altitude, temperature, and phase of matter. What we see from above is only part of what exists below. And still, we continue to look because the real discovery is not a single molecule or a single signal. It is the realization that chemistry itself may be more expressive than we assumed, more persistent than expected, and more universal than our models allow. Titan does not answer the question of whether we are alone. It deepens it. And in that deepening, it reflects something essential about us as observers. We are not just measuring a moon. We are learning how to recognize what the universe tends to do when given time, energy, and matter. And we are still listening.